I have the pleasure to introduce our CPH speaker today, Ngoc Truong. He is not very far from us, just about 1 hour, slightly more than 1 hour-ish down south in San Antonio, or 2 hours, depending on your luck. Yeah, he joined SOARI in San Antonio since 2023, and before that, Ngoc was in Cornell University. He received his PhD in 2023 in planetary science. Yeah. And yeah, and today Ngoc is gonna tell us all about solar abundances.
Yes.
Let's welcome Ngoc.
All right. Thank you so much. It's my great pleasure to be here, and thank you for the invitations. And this is a very lovely campus. So yeah, I'm going to talk about the solar abundance problem today and what has been going on with the discrepancy between different measurements for the past 2 decades, and what does that mean, and some implications for planetary origins and habitability. And of course, the year 2024 is a great year for all of the solar activity. We have the total solar eclipse in Texas, and I hope that you got a chance to witness something spectacular, or just feel the existence of the total solar eclipse. So why solar abundance is things that you care about, or I care about most, because to me, it's not just a very technical problem or technical detail. It actually, even think about the solar nebula as a cosmic soup of gas and dust, where all the planets and moon form from it. So the solar abundance is the ingredient that determines the right flavor, whether what is your whether it's your favorite type soup is, you need to get a right ingredient to get a right flavor. So, and with that said, the heavy element abundances have been used in planetary and exoplanetary science for the planetary origins. It is the measurement done by Galileo probe of Jupiter, which was argued that perhaps because of the similar enrichment of noble gases, carbon and nitrogen, then maybe Jupiter should be bombarded by cold planetesimals that form beyond the sea or snow line. Whether that's still the case, it was under debate, even with Juno, because one of the mystery is we still don't really know what is the deep oxygen abundant in Jupiter, even with Juno. And of course, it's been commonly said in exoplanetary science, especially with JWST now, that we can use the C2O ratio as a tracer of planetary formations. In terms of habitability, the radiogenic hits, how much potassium, thorium, uranium, all the radiogenic hitting elements, depends on which planetary system or which star you are on. It will determine mantle convections and plate tectonics, all kinds of activities. And we suggested that, maybe too much radiogenic hits is not really good for exoplanet habitability, because you generate no dynamo. On Earth, we also know that there are some microbes that found in Earth, in Canadian Kidd Creek mine, is where a mine that is deep 1.5 kilometers below the surface, so there's no sunlight, but we found microbes there, and and the water there is fairly old. It's 1.7 billions of years. So radiogenic elements actually decay would provide oxygens and hydrogens and all of the energy sources that actually have a microbe to survive there. And so in the later part of my talk, we'll see how it would potentially be applied to Europa liquid water habitats. So just to summarize, there's a wide range of applications. You use the solar abundance as a benchmark for understanding other star compositions. you want to understand how planets form, what elements it contains, and ultimately their potential to support life. And so traditionally, meteorite have been a source to provide us information about the elements, heavy elements, and mostly for refractory elements like silicons and aluminum, magnesium, iron, etc. The volatile elements like hydrogens, heliums, and noble gases are largely lost in meteorite, so you can't really infer that just from meteorite. And complementary to meteorite, we have spectroscopy, which probe the photosphere of the sun. And also helioseismology, which probe the internal structure of the sun, looking at the surface oscillation, and then you can really precisely determining the boundary between the convective zone and the radiative zone, as well as the helium abundance, which tells you about, which you can infer from that, the heavy element, the total mass fraction of heavy element Z. So what has been going on for the past 20 years, and what's the discrepancy? So early in the 80s, of course, on the spectroscopy model using 1D LT model or 1D non-LTs, etc. But basically, mostly 1D model. Starting from 2005, so this is an example, oxygen abundance determined from under Griffith 89, Griffith 198 using 1D model. And then the second chain came in 2005 where Asplund using 3D solar spectroscopy model revised out the abundances of several heavy elements. In this case, oxygen is reduced nearly 40%, nearly by half. And overall, over the year, as from 2009, 2021, has slightly revising the element a little bit up there. The same chance is also for carbons, etc. Now, what the consequences of that is, even with early 1D model, even in a very simple model, you have a pretty good agreement between photospheric spectroscopy and helioseismology. So the y-axis here showing the helium abundances in the convective zone, and the x-axis here is the real distance of the convective zone. So in other words, it shows you the boundary between the convective zone and the radiative zone. So 1D spectroscopy model, there's a lot of simplification in it. However, showing a pretty consistent with what helioseismology was determined. In contrast, when you revised out the heavy element abundances of oxygen, carbon, and several other, suddenly now there's no agreement anymore. And this has been the issue for the past 20 years, because technically when we thought that, yeah, 3D model should be better than 1D, right? So now what's going on? And there have been various solutions, people trying to propose that, increasing heavy elements a little bit by even Asplund 2009 and 2021. So the discrepancy is less terrible than 2005, but you still don't have the agreement. So just to show you a big background picture, the solar abundance is a complicated problem. It connects with a lot of models. We connected helioseismology for those models, opacity measurement, etc., etc. So one of the potential proposed solutions that people have proposed is how to make up for the decrease of heavy element is, what if the opacity that for each element that we have been using in theory is wrong? Maybe the opacity of elements is higher than what we would expect from plasma opacity theory. And if that's the case, you could make up for the decrease of heavy element just by increasing the opacity, right? So that is actually the work that have been done recently by the whole idea of the experiment is that you have a thin iron foil. So this experiment only done for iron. But the idea is that you shining a very high energy electromagnetic pulse into a thin iron foil so that you could ionize iron into the sun interior condition, which is million Kelvin. And so you basically took transmission spectroscopy of that, and you compare the opacity from the measure experiment with theory. And it suggests that perhaps at the X-ray wavelength, so the red one is, so this is all of the experimental data, and the blue line is the predicted theory. So it seems like, at least for one experiment, it suggests that perhaps at least at the X-ray wavelength, the opacity from experiment is actually higher than what we would expect with theory. However, that's only one experiment, right? So you have to see whether you could reproduce the results or not. And surprisingly, well, first of all, is reproduce the results for iron. So this is the data, and this is what theory is reproduced with the previous experiment. The surprising thing is that when you did the experiment with chromium and nickel, which if you look into the atomic structure, chromiums and nickel have very similar to iron. And you would expect that, wow, if iron behave differently than what theory predicts, and so they are chromium and nickel, right? But then surprisingly, you see that chromium and nickel behave exact same thing. So what's going on? Is it just iron doing something funny, or is just like the experiment have other issues that you haven't been identified? That is still a lot of effort that people are putting into that. And so those two previous experiment was done at San Diego National Lab in New Mexico, nearby here. And then there was other experiment using laser beam at Lawrence Livermore, and suggested that perhaps the iron opacity would agree with theory. And so now we have multiple experiments that don't agree with each other and don't agree with different experiments. And so the problem is this would become more opaque. But people are still doing that. So, if there's anything new, we will certainly hear about it. All right, so that is what we currently with the solar abundance problem. So now the question is, how do planetary scientists like me has anything to do with this? And yes, actually, we had a very close connection because, like I mentioned earlier, the solar abundance actually controls planetesimal condition. And as I will show in the next couple of slides, not only the abundances, but the redox of the nebula. In other words, how elements being distributed between different reservoirs in nebula, where the carbon is in reducing form like methane or in oxidized form like CO, that also controls planetesimal composition. And so there's an opportunity to connecting what we know from primitive solar system body with the carbons and the oxygen abundance of the sun. So today I'm going to talk about a couple of different primitive solar system bodies. First one is going to be Kuiper object, and later on we're going to talk more about CI chondritic meteorite, which we just returned sample not a long time ago, just last year with Ryugu and Bennu sample. But let's go first with Kuiper objects, because there are distant objects that are beyond the orbit of Neptune, and so there are cold conditions. There are some of those might preserve primordial signature from the nebula. And of course, there are a couple of objects that are really well known. Pluto and Charon system, we will be visited by New Horizon. Eris is, of course, another famous one, the one that the first capable object that later on we kind of demoted Pluto as a planet. Monkeys and Haumea is a very interesting one. It's like golf, like a football, and it's been really, really fast. So As I mentioned, here's Pluto. We precisely measure that with new horizons. Anyone in the audience want to guess what object is this? Any guess? Wrong guess is better than no guess. Actually, it's the surface of comet 67P, which was just a mantle that were visited by Rosetta. And comet 67P is a Jupiter family comet, so it's a unique form also in the Kuiper belt region. Talking about Pluto, is Pluto and Charon is, even though they form the outer solar system object, very distant, they are a rock-rich system with mostly, roughly speaking, 70% rock, 30% ice. Of course, we have to count organics and other stuff, etc. But it's mostly a rock-rich system. They form by the low velocity collision. So the impact is not actually making up the whole system. Didn't actually heat up the primordial Pluto and Charon enough to melt water ice, and therefore we would expect that Pluto and Charon should preserve the primordial signature. Another example is Triton, which might be which is of course a moon, a large moon of Neptune, which perhaps may be a capture type of object and might be similar to the Pluto line before capturing. So how do you explain the rock-rich nature of the large Kuiper belt object? So this is the current thinking. And I said the current might not be the most current, but this was the calculation done in 2008. So given a set of solar abundances, whether it's from 100 Griffiths in 1989, Cameron 1981, you will see that every 5 years there's a new table of solar abundances, right? And I think that when I said about this topic to people, people said another table, and then we have to go back and revise the paper. So, but basically, all of those data set, while under Griffiths, while the C2O is about 0.45, but roughly speaking, we have Pluto and Charon, which is density is roughly 1.8, so Triton density is about 1.9 gram per cc. And then Pluto Charon is about 1.8 in the region. So in order to explain the rock-rich natures of large Kuiper belt object, what we would expect is that you would have the nebula had to be pretty oxidizing. Most of the carbon had to be in the form of CO list, which the rest could be methane or organics. Similarly speaking, if you look into how carbon could be partitioned in different reservoirs, how much carbon in CO or organics or methane, you can see that if the nebula, if all the CO being converted into methane, then you would have a lot of water being available. And as a result, you form the system with much more water ice than what you would expect for Kuiper belt object. On the other hand, if you have CO and the rest of that is made up by refractory organic, you could explain the rock-rich density of the object. Now, what you will see from this calculation is that the density of Kuiper belt object depends on how much carbon is in the form of organic, the things like soup, basically. But you see that here, all the constraint of how much carbon in the form of organic in the nebula is unconstrained. It could be anywhere from 0 to 1. So what's new have we learned from that? So as I mentioned earlier, we have measurement, institute measurement for comet 67P as a Jupiter family comet forming the Kuiper belt. And what Rosetta found that in the dust grain of the object, carbon is make up quite a bit. The carbon to silicon ratio in the gas is roughly speaking about 5. And so as a result of that, you would see, and in comparison to the current carbon to silicon ratios, that we commonly use is about 10. So in other words, organics, refractory organic would make up half of the carbon in the nebula, in the type of object forming region. What would be the consequences of that? Here's a similar calculation to accept. Now we have the constraint of comet 67P used as a compositional model for how much organics would be in the nebula, in the KBO forming region. And as a result of that, you see that now organics would make up a very large fraction of carbons in nebula. And when you have a lot of carbons in the form of organics, you have more oxygen that being freely available to form water. Instead of CO or CO2, where one carbon you bound up with one oxygen. So as a consequence, this is the density of Pluto, Triton, and all these large type objects. Since it frees so much oxygen to form water, now you cannot really produce the dense rocky natures of type of object. So the takeaway here is we have the downwards revision, we have this discrepancy between helioseismology and spectroscopy measurement, so composition. And yes, increasing opacity is one of the proposals that I've been putting forward. But we need more experiment to really confirm and of course, understand exactly what might be the missing physics. On the other hand, we can also look at primitive solar system body, and especially the role of refractory organics has largely been overlooked in the current literature. But here we show that it actually could make up a significant abundance in the nebula. And as a result, the current C2 of 0.5 or 0.55, you really cannot reproduce the rocky nature of Kuiper object. And it's actually highlighting the solar abundance problem. And so I have a quick question for the audience. So we have mentioned what happened, what have we not mentioned so far in this block? So we talk about helioseismology, that is a problem, right? We talk about photospheric model. We talk about opacity, right? We talk about abundance, of course. Yeah, so now we only have the neutrino and the nuclear reaction rate, which connected to each other. But yes, solar neutrino is the one that we haven't really mentioned. So the next couple of slides, I will show you some of the new observations from neutrino that might give us some insight about the carbon and nitrogen abundance. Coincidentally, before I started my graduate school in 2017, actually, I was in a seminar. It was very random. It was in a physics department, but I was curious about different random things, and I'm still curious about random stuff. I went to a seminar that even in 2016, just a year after the Nobel Prize in Physics were awarded for the discoveries of neutrino. In particular, they found out that neutrino is a massless particle. That is a common assumption in standard physics model. Initially, it was added just because of we want to conserve the energies and the momentum. So it's a ghost particle that only exists in the mind of theorists. So, but eventually, and I won't get into the whole detail of that because that was something that John Bacon probably talked about that every year. That that be the solar neutrino problem in the sense that the theory of solar model can really accurately predict the neutrino flux measurement and so on and so on. It had been an issue until people actually found out that it's actually massive, small amount of massive. And you may say to me, wow, it sounds like something exotic that I never interact with. And it is true, you never really interact because the cross-section is so small. But in fact, it's also generated by very common reactions on Earth in reality is also generated from radiogenic heating elements decay, things like polypotassium, thorium, uranium. And what is really cool about that is, let me share a quick fun fact that every second, about 1 million neutrino cross the square centimeter of the Earth's surface. And so what's really cool about that is you could use the neutrino flux from the geoneutrino management to probing the deep mantle abundance of potassium, thorium, uranium, which I think is really amazing synergy between particle physics and geoscience. So as we know, the CNO cycle operates in the sun, right? I mean, it's not the most cycle that produce the most energy. Carbon, nitrogen, and oxygen simply plays a role as a catalyst for the nuclear reaction. But one of those byproduct is the neutrino. And so there's an opportunity that you can use a solar neutrino to probe to determine the CNO abundances. In 2020, there have been a couple of papers. The first one is the experimental evidence of neutrino produced in that cycle within the sun. And in 2022 and also 2023, they have been using the neutrino flux from the CNO cycle to actually deriving the abundances of carbon and nitrogen. What's the result show? So in this here, so the the horizontal axis showing the carbon, the total carbon and nitrogen abundances relative to hydrogen, and the y-axis showing different measurements that have been done before. So this one is the Griffith in 1998, the 1D spectroscopy models in in 2009, 2021. There's also a new spectroscopy model by Mario in 2022. This is a group from Maxwell in Germany that's revising up the abundances of carbon in the photosphere. Now, how does so neutrino measurement work? What they did is that what we could measure is the flux of carbons in nitrogen neutrino flux coming from the deep interior of the sun. And so you have to calibrate that using other neutrino flux as a thermometer to control the temperature interior. And you are accounting for the elemental diffusion because we have the convective zone, and then you have in the radiative zone, the elements simply got diffused over 4.5 billion of years. So after you are accounting for the elemental diffusion, you can directly compare the neutrino flux experiment with photospheric measurement. With the Boresino experiment in Italy suggested that perhaps you should increase the carbon and the nitrogen abundance in the photosphere should increase. All right, so that is an experiment. How about oxygen? Unfortunately, there's no oxygen measurement yet, but we have other measurement from Genesis, which is a solar wind sample that returned by it's a solar wind sample that returned by the Genesis mission. And what is nice about that is, of course, in order to deriving the oxygen's abundance from solar wind, you have to accounting for how it's being ionized in the photosphere, which is not a straightforward problem. But for oxygen, coincidentally, the oxygen have a similarly ionization energy compared to hydrogen. So roughly speaking, the oxygen to hydrogen ratio in the solar wind is just preserved from the photosphere. And so if you compare that, the data from Genesis with the new data from Mario 2022, there might be a little bit of overlap, but it's clearly increased comparing to Aspirin 2009. So now with those data, we can revisit what would be the prediction for the primitive solar system model for comparable object. Now, see, if you have more increase in the carbon's abundances, now organics in the nebula, at least in the Kuiper forming region, would play a less important role. In other words, there's more carbon in the nebula. So now it's only make up about 30% of carbon in the nebula. The rest could be in CO. And as a result of that, this is a range that we predicted, anywhere between 1.7 to 1.9 grams per cc. And so it would be consistent with Pluto and current density, also Titan as well. So this kind of intriguing, right? That the predicted density are consistent with KBO. Let me see how to play. And all right, I can't close this
Try
one
on the
up.
tray underneath the.
Yeah,
See, it's
it's
mouse.
a mouse.
Oh, all right, here it is. All right, we make it easier to see. All right, now it's better. Yeah, so kind of intriguing that you could reproduce Kuiper object density with this new abundances. But how about other body, right? That would be the next question. So thankfully, we have been having a couple of sample return mission from carbonaceous chondri. In particular, the CI chondri that is the most transforming the outer solar system. The one on the left is Ryugu, was an object that was returned by a booster 2 missions. And the one on the right is Osiris-Rex. It was returned last year to asteroid Bennu. It's kind of amazing that you could return sample from Bennu. If you see on the picture of the geology of that asteroid, it's terrible. There's nowhere to land. So those meteorites are very interesting in the sense that they due to Jupiter formation. So let's see whether I can play the movie. Yes, I can play the movie. So probably due to Jupiter migration, it will eventually open a gap in the nebula that effectively separating out two populations of meteorite. One is the NC, the non-carbonaceous, and the other is the carbonaceous one, will form in the outer solar system. So there is a gap that will open when Jupiter was formed. So carbonaceous chondrites will form the outer solar system. They contain more carbons and organics than the non-carbonaceous. And of course, they contain more water as well. So what do we know from the sample, right? So this is, roughly speaking, a brief history of how Ryugu came to be. Initially, you have just a bug born of rocks and ice and minerals and stuff that came together into the asteroid. And then when you assemble together and you have radiogenic heating, it's become melted, right? Water melted, become liquid water, and eventually you have aqueous alteration that happening inside this body. So what you see today is not the primordial one. What you see today is the result of aqueous alteration happening earlier in the history of Ryugu, which is hydrosilicate and carbonates and all kinds of aqueously altered product. And this is the one that you found on this sample. So one of the conclusions is that, roughly speaking, the sample are really similar to CI contract that we return on Earth. What is the differences? The differences between those samples is that on meteorite, in carbonaceous chondrite on Earth, we found sulfate instead of sulfide. What does that mean? Sulfate is the aqueous alteration product under oxidizing condition, right? And so oxidizing condition is Earth today, at present day, is an oxidizing planet with O2 on top of that, right? And the absence of sulfate in those samples means that there was a portions of meteorites that we retrieved on Earth have been contaminated, either by water vapor in the atmosphere, due to whatever sample retrieval that you have, We don't know, but we do know that it was contaminated from Earth. What does that mean? That means that in order to connecting the soil abundances with the primordial water abundance of body, you have to account not only for the water that you saw, that we see today in the sample, but you also have to accounting for what have undergone aqueous alteration. And so I don't expect everyone else to read all of this. The whole idea is we have to revisit in order to inferring the primordial water abundances. You have to accounting for all of those components. So not only water that we see today, but the waters that have been aqueously altered and now being in the form of carbonate or in the form of other oxide or sulfate. And that is one that typically been done to accounting for the primordial water abundance. Sulfate is no longer present in Ryugu sample, right? And because it's not and also the oxygen in sulfide now majority of those is in sulfur as a carrier. So instead of being oxidized, as a result of that, the total primordial water abundance in the sample are actually less than what we previously estimated for CI contract on Earth. And as you could get, there's a relationship between the solar C2O ratio with how much water you would expect in the body, right? And so this one to show you is about the total water, basically. I scaled that by silicon, but really the one on the left is how much water do you have primordially. And similar to the previous calculation done for Kuiper object, it depends on how much carbon in the form of organics. And this is the range of prediction for CI. And this show a consistent with Ryugu, both CI and Ryugu will show a consistent with the increase in the solar C2O ratio. So to summary, if you're increasing the carbon, nitrogens are also together, the total mass fractions of heavy elements, which we denote here as Z. So Z is the total the mass fraction of the heavy elements, X is the mass fraction of hydrogens, and Y is the mass fraction of helium. So this is the classical value, right? And then after revision, this is the current value that currently adopted. The new spectroscopy model revises up again, and then this is the results for my model. And this would also produce some prediction for future helioseismology's model to test this prediction. But I did a simple calculation that given fractions of Z that we have and the Z of X, it seemed like we might be able to get some consistency, at least some overlap with the surface helium abundant determined from helioseismology. So the paper was accepted about 2 months ago, and then it's going to be in press this week, and you could definitely buy that on archive. And for the future, this is what we're going to, there are going to be a lot of neutrino experiments that not only for helioseismology measurement and cosmochemical measurement, so neutrino would probably play an important role for this kind of analysis. And by the end of the year, we would perhaps expect that there are going to be some post-like data from one of the neutrino experiments in China, and US would have a couple more as well. So to summarize, there is a quick summary of this session. Is that, by employing a new set of data from solar neutrino and solar measurement, we could probably have, it would predict, is it would produce the rocky nature of type of objects. And also the lack of surface and terrestrial contamination in Ryugu and Bennu sample suggests that we have less water in the primitive body, which would be consistent with the increase in the solar C2O ratios. And we can test that with other measurement. So as the earliest part of this talk, I mentioned about the works of Harold Urey in assembling one of the first tables of abundances. But in fact, the most famous scientific work that, well, he has done a lot of impact scientific work, but the one that awarded him the Nobel Prize in chemistry is about the discovery of deuterium, one of the isotope of hydrogen. And the new age, deuterium to hydrogen is an important measurement in cosmochemistry and planetary science. Your different part of the nebula actually has a different DOH. And here in Austin, there's also a very cool measurement from JWST with the DOH measurement of a brown line. So the question here is, now let's say we have a updated solar abundances, what problem that could be solved with this? So in the last 10 minutes, 5-10 minutes of this talk, I will give some of the example of some of the implications for understanding planetary origins and habitability. One of the first questions that I'm interested in is, what is the nature of Uranus? How Uranus was formed, where was it formed into this? And the DOH is one of the important constraints because you can see the difference, it varies whether you are a CI from primitive material like meteorite or comet. One of those, and Jupiter and Saturn is mostly gas giant planets, and so you would expect somewhat similar ratio with the protosolar. Now, there are lots of mystery that we don't know about Uranus, but one of them is why we've been commonly referred to Uranus as an ice giant. Why the DOH of Uranus and Neptune is so low comparing to all the other icy material, right? Comets and all of those things have way higher DOH. So what's the problem here? It's, while of course there could be something that is not well-smig in the interior that is a possibility. But I wanted to point out another intriguing possibility that the only time we have ever visited Uranus and Neptune was back in the 80s with the Voyager, right? And we look into the C2O, so we're determined back at that time with undergraduates, it's very low, it's about 0.45, right? Even until, yeah, we revised that up in 98, it's about 0.5. But back at that time, it's about 0.45. A C2O ratios of 0.55 definitely imply that the planetesimal composition is mostly high-rich. And that's how we commonly assume the nature of the Uranus and an iron giant, because we think that, oh, it's from the outer solar system beyond the sunlight, so we need to have high-rich material. But now when we know more and more about primitive solar system material, Pluto and Charon, after all, is a rough-rich object, right? And that is also, and you can see from the trend here, and also microphones, you can see that it also increased over time, which implies that perhaps you might have an object that is more rock-rich in nature for Uranus than we think it is. And not only, we have only talked about rocks and ice so far, right? Organics is also an important component of planetary building block, especially, and I had mentioned earlier with comet 67P. Beyond 20-30 AU, that's the area where it's kind of an object will form. There was much abundance of organics, Halley, comet Halley, comparing to CI chondrite, for example, right? So we don't know whether Uranus formed in situ or it's formed closer to the present location and migrated outward. But one of the insights from cosmochemistry is that if you form things in situ, then the planets may migrate a lot more organic than if you form at a region that is closer to the sun. For example, when CI off, CI connect with fossil. And we look into the derivation of organic, and I apologize for this very complicated plot, but here is the, let's see, yes, so the derivation of refractive organics can also be measured by comet spectroscopy. It's way more in hand, even though it's about 10 to minus 3. So it's 10 times more than the Earth's ocean value. And roughly speaking, 3 times higher than CC comet. So as a result of that, you form Uranus, and in a similar sense, Neptune is the current location, 20, 30 AU. You might expect them to create a lot more organics, and effectively, it would massively raise your rate. That might not be, that may be even extend this discrepancy between what we measure in the atmosphere. How about the Galilean moon, right? Every time I give this talk, people ask, how about the Galilean moon? Because we think about capable object is not as high rich as some of the Galilean moon. And I'm not talking about Io, Europa. Io has no water. Europa is an ocean once everyone talk about, but in planetology point of view, there's not so much water in Europa. There's a little bit of water. It's a terrestrial planet. On the other hand, you have Ganymede and Callisto, which has a lot of water. And roughly speaking, you have equally amount of water compared to rocks in Ganymede and Callisto. So how do you make more water in the European nebula? What's the evolution of that? So there are a couple of ideas. One idea is a very classical idea from the 80s that perhaps the subnebula surrounding Jupiter was dense and hot enough, so you have enough temperature and pressure that you could effectively converting CO to methane to make water. That's one way to make water, right? But now people, it is still a hypothesis to be tested, but now people was more believing into the idea that maybe the subnebula is not that dense. So how do you make more water from that? So one of the idea is perhaps you would form at the Europa forming region. It's way harder than Ganymede or Callisto. And you can imagine somewhat a imaginary water snowline here in between Europa and Ganymede. So the idea here that perhaps that area could be Europa form closer to Jupiter, and so temperature in that area is higher, that you could perhaps dehydrate the phyllosilica, silicate, which is the hydrated silicate in those areas. And when you do so, the water vapor in that area diffuses outwards. Going back to the colder area, we condense back. That's how we could make more water in the in Ganymede in Callisto, in comparing to capable object. How to test the idea? Now, if water be vapor being equal to vapors within equilibrium at the Europa regions and being transported outward, you would expect a very low derivation. Roughly speaking, similar to the protosolar. And I'm sorry for another complicated plot again with a bunch of other things. I started to staring at this plot from in Glasgow. And at first I thought that you look into the constraint for Callisto. This is the derived constraint for surface ion from the nearby spectrometer on Galileo. And you could see that, it's one order of magnitude. That's the Europa, right? It could be similar to Canadian chondrite, it could be similar to comet over here. The point here is that the Europa is so large that when I look at that in graduate school, I thought that we can't do anything useful with this one. But now I recently rethinking this again, and I constantly appreciate more this complicated plot. So the idea is that depending on what type of material that you created into crystal organisms at first. But as you add more water over time, which has protozoal value, you will decrease the overall pH. If you start out with mostly comet to the water, you could add 80%, pretty much. You could make an object with mostly water ion, and you still be able to satisfy the lower limit constraint from the Galileo data. But if you're starting with just combination chondrite, you could add a little bit more water, but it's not as much to produce the ice-rich contents of Ganymedes and Callisto. It means that either you need to add some more comet or you need to add some more organics. And so that would determine what will be the initial volatiles and organic content that we have at first. In order to determine the all other parameters, the potential habitability, for example. And that could be tested by various instruments on Kuiper, like the mass spectrometer or JUICE, with not only the mass spectrometer, but also the sub-millimeter wave instrument, similar to Herschel. And also with JWST, we have found dew variance in ground dwarf, we saw dew variance, we measured dew variance in Kuiper ball objects. I know that people have put in proposals to do that for observing with JWST. Don't know whether they will be success or not, I hope. So, and I also don't know whether it will, what the Europa is. But I want to go very quickly on.
Yeah, we're almost out of time.
All right,
Yeah.
so I think I will probably stop here. I will mention very quickly the idea of how you produce oxygen. On Europa, we commonly talk about oxygen as produced on the surface. And you transport downwards, and this is work done by Mark Hesse here. But alternatively, you could also produce oxygen in situ just by radioactive decay. Also, active element just producing high energy electrons and radiations, and you could breaking down oxygen, etc. So I have been investigating some kind of process and how important it is. It possibly may play a role as a potential for chemical energies. In my chain, the chemistry is a pledge. And I want to end with this one, which is the recently launched of Europa Kuiper. We had hurricanes and we have tornado. I and several others were stuck in the hotel. I thought to myself, well, I'm so stupid, but eventually it's now on its way.
But we have a class, but we should still
Yeah.
have one question.
Yeah, we have a few time for one or two quick questions.
Anybody in the room?
Yeah,
So
can definitely contact me.
Yeah.
Yeah.
if,
Excellent.
if people have questions, please feel free to email Ngoc afterwards, or contact me and I'll forward the email.
Excellent. Thank you.
Thank
you.
you.
Thank you.